Hello, everybody. I'm Andrei, and I work for JetBrains as a Senior Vice President of Investments, Research, and Education. Welcome to Regionals. Great things happen when great minds come together. JetBrains wants to seek out great minds all across the globe, support their initiatives, and work together to create great things that will make the world a better place. That's why JetBrains is proud to be a Global Tools sponsor of the ICPC. There are already many great minds working at JetBrains, and together we have created some amazing things, like the Kotlin programming language, for example. It keeps on growing and growing in popularity. In 2017, Google began officially supporting Kotlin as a language for writing Android applications. We have also created professional development tools like Cline for C++ programmers, IntelliJ IDEA for Java, PyCharm for Python, and also educational tools that help people learn and teach programming. The regionals are the biggest contest in the ICPC calendar. Thousands of talented people all over the world team up to solve complex real world challenges. These contests are the proving ground for future champions. But even if you don't make it through to the finals, the experience of competing in the regionals and the new friends you'll make along the way are priceless. Enjoy the ride. Best of luck to everyone.
Innovation is a journey of doubt and uncertainty. From 5G deployment and its ecosystem came digital transformation in all industries. From Huawei Cloud came the wonders of widespread remote healthcare. From AI machine learning came better, more intelligent ways to protect the Earth. From AI computing came advanced astronomy research and a deeper understanding of the cosmos. From new ways to live, a greener Earth, and futures beyond our imagination. Our journey of innovation will never end.
There are parts of our world where light can't reach. Divides that are too wide for rivers to flow. But technology has the power to help. In remote areas of Nigeria, connectivity brings new life to local communities, opening doors to trade, banking, better education, and healthcare. In Bangladesh, digital training has given more than 240,000 women new opportunities in life. With AI, deaf children everywhere can translate written words into sign language. So no child misses out on the joy of storytelling. In Central America, upcycled smartphones help rangers detect poachers and loggers, keeping rainforests safe for everyone. Our planet may not be perfect, but digital technology can help make it better. In the next 5 years, we want to work together with our partners to help 500 million more people directly benefit from digital technology. Focusing on healthcare, education, environmental protection, and economic equality. Tech for all. Pass it on.
It was the first time we had this kind of a participation in the history of ICPC. And again, it is followed before the regional contest, the 700 teams, it is for the first time. So what I wanted to convey is the problem setters here, who have gathered here, have put an enormous effort to make sure that the contest has its own quality. it is not just about the participation in ICPC regionals, but also about your thought process, the way in which you think. It has to change. So the problem setters are instrumental in changing your thought process, because problem solving is again a greater skill that will shape your career. And I'm sure that almost all of you who participate in ICPC will look for higher level jobs. So let me take this opportunity to congratulate and thank Balaji Ganapati, who managed the contest very well in this very new platform, codedrills.io. The very beginning, when I started planning for ICPC, I told Bala that I want to host this contest in Code Drills, because of the reason that as I mentioned, he is a ICPC world finalist, and when he starts a platform, I wanted the first contest to be ICPC at this level, and we made it without any glitches. And thanks for that again, Bala. So this opportunity, let me take this opportunity again to thank the problem setters during the busy schedule, and of course during this pandemic time, with a lot of I won't say that issues, but the situation, the demand of the situation, they have spent enough time, they have put on a lot of effort, that made this contest a quality contest. So that said, let me hand over the baton to Bala again. He said that he is a little sleepy, so he may not be taking too much of time. But yes, there are our problem setters, the judges, who are lined up to explore the different solutions to the problems we had posted in the regional contest. And once again, let me take this opportunity to congratulate all the teams who participated in prelims as well as in the regional round, because you made it possible even during this time, and wishing you all a very bright future. Thank you, Bala. You can take over the stage now.
Hi everyone. Thanks for joining. And yeah, so I would just like, before starting the discussion, I would just like to say that mostly when we are when we really start, usually I always look to build a setting team, and how ICPC really works is, with respect to setters, is that usually the past participants, they always join and try to set and test the problems. And I think this time there was some difficulty in getting enough setters, mostly because I guess the 2020 ICPC, we are just now wrapping up 2020 ICPC. So I guess it's obvious why there are not many setters. But yeah, usually also I would really like to see a lot of setters from the community, especially those who are graduating now or completed the ICPC season. It would be really great if many of them join back and give back to ICPC, and anybody can help in many ways. Setting, there is testing, there are lots of work that goes on behind the scene to conduct a successful contest. I think this time we got lucky for with regards to testing, mostly because there was no ICPC for schools. So we managed to get the IOI gang, Kshitij, Udit, everyone to test it. But I don't think we will be that lucky next time if there is ICPC for schools. So yeah, we definitely want a lot of people, a lot of current participants to join and basically help us with the setting part. Yeah, so I guess there's a Q&A now. Yeah, I think it's very predictable what the question would be. Yeah, anyway, so I guess let's get started with the discussion session. Oh wait, I think Deepa, would you like to speak something? I think so. Deepa was also working behind the scenes a lot and making sure everything was going well and everything. So I think like she would also like to say a few words before we start this session.
Yeah, hi everyone. I wouldn't take a lot of your time and we'll keep it short so that we can move on problem discussion. So this ICPC season has been such a great learning experience for me. Like I learned how to plan, execute, track, and manage such a huge project. Like when Sir told us that they are planning to hold the regional on Coatis, there was like only 2 or 3 months left. Obviously, it was before all the postponements. So getting platform ready with all the required feature within 2 3 months, it seems impossible at that time. So one of the main things that I learned was how to approach a project when it seems so huge and vague. The first thing we did, like we break down all the tasks and into small tasks, and we tried to design and execute as much as possible in a single day. So there was like 75 tasks that we needed to complete before the regionals. So it was kind of a lot of load. So the second thing that I was learned was the importance of iterating over the side features. So instead of completing all the features and then holding contests, what we did, we try to complete some features and then host some contests, get the feedback from contestants, and iterate over those feedbacks. So we did this, and it was a smooth process, and the experience was smooth to the contestants. And the third thing that was like how I learned that how to manage stress when conducting such a huge event. And this stress was not just because of the workload, it was also handling, because due to handling users. And at the end, I would like to thank Maheshwari sir for constant support and guidance he gave us, and for his belief in us. And I also like to thank our team, our admin, setters, interns, and testers, who all together made this possible. This, I think, this is just the beginning of Codrills. I'm sure there will be reach new heights in coming days. That's all from my side. Thank you.
Yeah, thanks, Deepa. So yeah, she did like a great job making sure all the features and that you see and requested were implemented in time. So I guess let's start the problem discussion session. Ashwin will be presenting the slides. While he's presenting, I'll just say, like, usually there's a lot of discussion that goes on behind the scenes. When selecting the problems, the types, the difficulty, we always look to make sure that there is a balanced, that set becomes very balanced, and there are a right amount of difficulty so that all teams have something to do, as well as like the topics are spread across the topics, and it's not like there's an overweight towards certain topics. So yeah, and just giving you an idea, like it takes a few iterations to get the problem set correct, and we always like till the last day we sometimes add or remove problems depending on the balance and requirement that we have. So yeah, I will say more about it as we go on. So let's start. Yeah, so the credits for the regionals is like thanks Vichitra, and I won't read everything, but yeah, I would like to call out Kevin, all the setters, Kevin, Ajinkya, Vichitra, and Webo, who all like came together and made sure that the all the problems were there and well tested. And the testers, special thanks to Kshitij and Udit for and like the entire IO gang. Like I don't think we would have tested properly without the IO gang's help, really. So most of us are like not active competitive coders in general, while we try to keep active. So testing is always an hard thing for us in general. So we always look for any who is active competitive coders to come and test it. So real thanks to all the IO gang. So yeah, let's go to the first problem. So the first problem has 700 plus accepted solutions. And I think almost everyone who participated solved it. And it will be explained by Varad, Thanos the teacher, the problem, and its author is Kevin.
Yeah, hi. So yeah, this was the cakewalk problem in the contest, and like as expected, it was like fairly easy. So yeah, let's discuss the problem once before going to the solution. So basically, we have you are given like 2n students with their skill levels, and we have to basically pair each student with someone else in such a way that the average skill level of all the pairs is equal. We had to basically say if it is possible or not, right? So we so yeah, so basically like it's basically just you have to understand that you have to like greedily, if you think, you just have to pair up the smallest with the largest, the second smallest with the second largest, so on and so on, because if you do that, the average will kind of be same, right? Like that is easy to understand. And yeah, I guess sorting the array and just picking the first and last and second last, etc., and doing that, and just checking if there's all the averages value to a same amount. So yeah, if that is true, then we just print balanced. Otherwise we just have to print perfect, and otherwise you have to print imbalanced. And the complexity is the complexity required to sort, which is n log n. And even as the constraints were very small, so even n square sorting would have passed. And I guess most of the teams solve this problem. So yeah, that's it for this problem.
The next problem, thanks for it. The next problem is the invasion of Balaji, which has 539 submission. Its author is Vichitra. And let me see who is explaining it. Sorry. Vichitra will explain that. Vichitra.
So, so yeah, we prepare this this image just to troll Balaji, but yeah, I think few of the setters are there. Next one. So yeah, the problem was like we are given two arrays, and we want to perform some operations at most m times. The operation is like replace the value of the first array equal to first array plus the second array's value for any index I. So that was the operation we are allowed to do. Then after doing this operation optimally at most m times, we want to find out the maximum subaberration. So that's what the problem says. But yeah, the statement was like written in some way that you have to derive like what exactly needed to find. I will talk about just the background of the problem. So the earlier version was just like we have to perform the action just one time, and we wanted to find like I think the problem was like much more simpler, just maximum value only. So that was like initial idea, but then we kept modifying it, and then just to fit in the slot for the second problem. So uh, so here like we want, so in the context of given problem, we have some soldiers which we want to train. The training is basically adding the two elements for the ith index, like first array and second array. Now like if after training the power is reducing, then obviously we want train. So basically we can consider all ti equals to max of ti comma 0. So that is like if our power already reduces, then why would us do that? Because at the end of the day we want to maximize the power sum. So yeah, the worst case answer is 0. So we would just initialize the answer with 0. Next slide. Yeah, then the second insight is like we can perform m operations, but in which soldier we should basically perform the given operation. So it's always optimal to train only one single person. Like why so? Let's consider the two soldiers Ti and Tj. So like these are the powers they will gain after training. So if the first case is like if Ti is greater than Tj, that means the ith person would get more. So we should obviously train the ith person instead of the jth person. Similarly, if Ti less than Tj, then we should train the jth person. And if both are equal, then we can train any one of them. Like so training I or J, or let's say sometime I, sometime J, it's like same in all the cases. So let's just take like we will train only I. So this way, like we can always say that training one person is enough in the optimal solution. Next slide. Now, like after looking at this observation, the final problem is very simple. The reduction is very simple. So now we are just given an array, and we want to perform an action on one particular index, and after that we want to find out the maximum subaberration. So that can be solved in many ways. So one of them is obviously this one, where like we will try training ith person. So when we are trying ith person, that means we obviously want to select the ith person. Then we will pick from the left side as many elements we can pick that such that the sum is highest. And similarly from the right side, we will pick as many elements we can pick. And then we will keep the sum of left, right, and the ith person plus then how many operations we performed. So m into whatever the gain we were getting after training. So that is the, now we can take the maximum of these things for all the I. That was the first idea. The second thing, it's like we can also do a simple DP where we maintain index and whether we have performed the given action or not. So that is like n cross 2 DP. So that's also possible. And the like one more idea here is I think we can also do segment trees. If someone wants to don't think much, you can just perform some range max queries, and by that way also we can do it in OF and login. So I think, yeah, best solution we had was OF n, and that should be it.
Yeah, thanks, Ishita. And let's see. The next problem is hackerland. And yeah, so now we go from cakewalk to a bit more harder problems. It's still an easy problem, but yeah, relatively harder. So, I'm sorry, let
So
me just see.
I'll explain Hackerland. So the problem was to given us n cities, and each city has a rating R or Ri. Each city has the rating Ri, and like if two cities I and J, I not equal to J, like if they had like GCD greater than 1, then like there will be a road between them, like bi-directional road. Now the objective was to connect all the cities. Like if it is not connected with the given rule, we can like change the Ri of like any city by multiplying it by k, and the cost is like k for that operation. So like with minimal cost, like we wanted to connect all the cities so that like from any city you can go to any other city. Like so that was the end goal. So like two numbers have GCD greater than 1, like if and only if they share a prime factor. That's one point to note. Then like to start with our solution, we know that Ri less than or equal to 10 power 6. So we, for every prime appearing, like every prime factor like less than 10 power 6, we create nodes. Then like we add an edge from the city I to P if like P divides Ri. Then like we want this graph to be like connected. So first like we will find the number of connected components in this graph. So and like if there is like one connected component S and like other connected component T, we want to connect it, like we can multiply like either one of them by k, some k greater than 1, so that like they share a like if they don't share a prime factor, like that's why the reason they came in like two different connected components, we can like do the multiplication to like make it connected. So one insight. So like if you multiply by non-prime k, like then we can actually separately multiply by prime factors of k. Like so x and y are prime factors and xy is k. Then we can actually multiply by x and y. So like here x plus y would be still less than xy, which is our k for any x and y greater than 1. So that's one like insight. The second insight is like we won't multiply a prime which is greater than or like equal to 5. So instead of doing that, like we could simply like put multiply 2 in the both connected components to make an edge between them, because like the proof is here. So 2, like if you're connecting t components or t plus 1 components by 2, like multiplying by 2 to connect them, so the cost would be 2 into t plus 1. And like if you are multiplying 5 is, we are going to multiply 5 everywhere, like it would be like 5t, so like or like pt for any prime. So pt minus like 2 into t plus 1 would like give to 5t minus 2t minus 3 and like 3 minus 2. Like so always like it's better to use like multiply by 2 everywhere, like if the prime is greater than or equal to 5. So now the remaining primes are like 2 and 3. Like so sometimes we will take 2 and sometimes we will take 3. But then like we won't use like 2 and 3 to build the solution at the same time. Either we use 2 or either we use 3. So like the intuition here is that like if we multiply one of the components by 2, then it's like better to use 2 to connect rest of the components to this component, rather than using 3. Like it would be still cheaper. So that's the one insight. And the last insight is like we won't multiply 3 by twice. So the proof follows a similar approach to the one for 5. So like if you are doing like 2 by 2, multiplying by 3 by 2 times, like it would be better to multiply by 2 by like 2 times. So like 4 is less than like 6, and like this is the same proof, like similar to this proof that we like saw earlier. So these are all the insights. So to formally state the solution, it would be like min of f of 2 or like f of 3. So f of p is the cost assuming we only multiply by p, and like f of p can be expanded as like p into c minus a of p. So c is the number of connected components in the graph that we prepared, and like a of p is like 1 if like p is already present. So we only want to add the p or like multiply the ri by p if like it's already not there in the prime factorization of ri. So everything can be done in like big O of n plus like p of total, where like p of total is the total number of prime factors of all ri, and like this can be like pre-computed, like so we can use a sieve to do the prime factorization for like 1 to v, where v is like approximately 10 power 6. It takes like v log v, v log v. Yeah, so this can be done well within the time limit. So that's pretty much for this hackerland solution.
So the next problem is peace, freedom, justice, and security. And where 137 accepted solution, it was a geometry problem. And thanks, Kevin, for Kevin or the author for that. And explanation would be given by Ajinkya.
Yeah. So yeah, before we begin, firstly, let's quickly look at what the problem was. So we were to find 3 points P, B, T, such that each of those points were some lattice points. That is, they had integer coordinates, and the pairwise Manhattan distance between each of them should be the ones that were given to us in the problem statement. So we were firstly, we had to decide if we could find such points, and if yes, we had to actually find those points. So yeah, before we begin, first let's try to see the cases where it is not possible to find any of such points. So yeah, as we can see here, firstly, if the distance from say P to B and the distance from B to T, if their sum is less than the distance from T to P, then this actually means that the distance from T to P is actually larger than the distance via a different route through P, and that is actually not possible, right? So for such cases, we would say that it's impossible to find an answer. Another one is a case where the sum of these distances is odd. And again, this is equivalent to starting from a point, say P, going through different routes, firstly to point P and then T, and then returning to P. And if we consider this as a walk along the grids, then we are just walking through the grid and then coming back to the same point that we started to. So again, this can only be achieved in an even number of steps. So again, if the sum is odd, then we can say that it is impossible to form such a triangle. So if we don't have any of these cases, we can try to find if a triangle is possible. And we say that it is always possible. Let's try to see how in the next slide, please. So yeah, as we try to reach to a solution, let's try to find some insight so that the solution is simplified. So firstly, we will begin by assuming that one of the points of the triangle is at the origin. And again, we can always start with this assumption, because at the end, we will just translate whatever triangle we get to the first quadrant, because that was another constraint in the problem, that all the coordinates should be in the range from 1 to 10 raised to 9. So yeah, we can just begin with the assumption that our triangle, one of the points of our triangles is at the origin, and then we will translate it to the first quadrant. And while we are assuming that, for our convenience, we can also allow negative coordinates if that help us in getting any of the triangles. So yeah, with this in mind, let's also move on. So yeah, we have already fixed one of the points at the origin. Let's also try to see if we can fix another point. So we state that if an answer exists, we can always say that there exists a triangle where two of the points are aligned either horizontally or vertically. That is, one of the sides should be parallel to the x or the y axis. And suppose it is aligned vertically, we can always rotate it again so that it becomes aligned horizontally. So we can also say that there is always an answer where the side of a triangle is aligned horizontally. And again, if that is true, so there will exist a side with coordinates 0, 0 and x, 0. We can also assume that x is greater than 0, because if it's not, we can just flip the triangle horizontally. So yeah, this sounds not very intuitive maybe. So let's try to formally prove this as well. So can we move on to the next slide, please? So yeah, let's try to prove why it is always possible to have a triangle where one of the sides is aligned to the horizontal axis. So suppose that's not the case, and we have a triangle which satisfies all our constraints in the problem statement. And let's try to consider a point. Let's rotate the triangle such that there is a point xy, which is the leftmost bottommost point of the triangle. Or in other words, both the x and y coordinates are the lowest for that point. And again, it will always be possible because there are only 3 points that we have to consider. So suppose we have rotated the triangle now and we have such a point xy. So the area of this triangle can be said to be alpha x plus beta y. And these alpha and beta are actually just dependent on the 2 points, the 2 other points of the triangle. And this can be said via the shoelace formula, which helps us to find the area of any polygon in the Cartesian plane. So if the 2 points are fixed, this area is just dependent on the leftmost bottommost point xy and some other parameters that are dependent on the other 2 points. So yeah, let's move on. So yeah, since the area was alpha x plus beta y, and remember that xy was the leftmost bottommost point of our triangle. So if x comma y is not yet aligned either vertically or horizontally to the other 2 points, we can always try to move this point in any of these 2 directions, where we either try to increase the x coordinate by 1 and decrease the y coordinate by 1, or decrease the x coordinate by 1 and increase the y coordinate by 1. So by doing so, the area will either increase or decrease by alpha minus beta, as we can see here. So in at least one of the direction, the area will either increase or remain the same based on what the alpha and beta values are. So it's always possible to go in either of these 2 directions such that the area is either increasing or remaining the same. And we can continue to do this as long as one of the sides does not become aligned to either the x or the y axis. Can we move on to the next slide? So yeah, we will continue to do that, and we will go in the direction where the area increases if that's possible, or it remains the same, but we will continue to do that as long as the 2 points are not aligned. So at the end, we will always reach a point where one of the sides is parallel to the x or the y axis. So just summarizing the whole thing, we had already fixed one of the points at the origin, and we also have proved that there is always a triangle where one of the sides will be parallel to the x-axis. So the next point can also be fixed at x, 0, where x is any one of the distances which were given to us. So yeah, let's move on to the next one. Next slide. So yeah, as 2 points are already fixed, we are now trying to search for the third point. And yeah, as we can see here, if the third point is moving along some line, this will mean that the height or the altitude of this triangle will also increase linearly. So what we want to do is the eventual aim is, if there are multiple answers for this, we have to find the triangle with the maximum area. So yeah, that is also one of the points that we'll have to consider. Can we move on to the next slide? So yeah, now the 2 points are fixed, 0, 0, x, 0, and we have all the 3 distances that we want to achieve. So there are some equations to solve, and we can get the 3rd point through that in constant time. Again, if there are multiple options, we will choose the one with the highest y coordinate, because that's what will give us the maximum area. So yeah, the only important point that we needs to be considered while implementing this is that the order of the points also matters, because the problem specifically asks that the distance between those points needs to be what it asks for. So yeah, while printing the points, we need to take care that we are printing them in the correct order. So yeah, basically that was it for this problem.
Thanks, Ajinkya, for the explanation. The next problem is lot of the group. Now we are going into the easy, mediums, and medium territory. And Kshitij will be explaining this. Author of this problem is Kiran.
In this problem, we have to find the number of subsequences such that for every pair of elements in that sequence, ai plus aj, there is an element with distance at most d. In this problem, d is at most 3. So the first observation is that there cannot be 2 numbers more than d. There some will be too large. We can prove this by contradiction. Suppose there are 2 numbers greater than d. We can take the biggest 2 numbers x and y greater than d. So x plus y will be greater than y plus x plus d and both y plus d. So it won't be possible to find any element with distance at most d. Similarly, without loss of centrality, we can also say that there cannot be 2 numbers less than negative d. The second observation is that if there is a set of valid elements and we add a number whose absolute value is at most d, we can add it, and then also the sequence will be valid. Because xi plus c is always close to xi itself. Next slide. So now the array consists of at most one value greater than d, at most one value less than minus d, and some numbers which are not contained in the previous two base. So there are 4 cases which are listed here. We take no numbers which are outside minus d to d range. The case 2 is we take one number which is greater than d and no number less than minus d. And third case is we take no number greater than d and one number less than minus d. And fourth case is we take both one number greater than d and one number less than minus d. The first 3 cases are easier to count with the case 4. So we can count the numbers which belong to each of the 3 ranges. For case 1, there are 2 raised to the power m subsequences, g actually. For case 2, there are 2 raised to the power m into g. Case 3 is similar to case 2, so it's 2 raised to the power m into l. The only case in which we have to do more work is case 4. So we can say that there are 2 numbers x and y, which are not in minus 2 to 3 range. The observation is that x plus y must be near to some number with distance at most. Now, given that x and y absolute value is greater than 3, greater than d, so that number which they are nearer to has to be between minus 3 and d. So with some math, we can show that x plus y must be between minus 2d and 2d. So now once we have picked the negative number, we can iterate over all the possible 2d plus 1 numbers and check each of them individually. Now the sum is, we can take their sum x plus y. Now to choose from the remaining numbers which are whose absolute value is small, there must be at least one number. So say the numbers are -4 and 7, and d is 3. Then their sum is 3, so there must be some number between 0 to 3 as well. So now we can, with some basic counting, we can count that. So once we have fixed the number, we can, there are many solutions. So one in this solution, one is the inclusion exclusion, in which we can count the number of cases in which no number is in that given range. And the second solution is we can iterate over all the mass. So since d is very small, the complexity will still be small. So our best solution till now, the inclusion counting one, is order d square plus nd. This can be improved faster with some more details, which have been left as an exercise to the reader.
The next problem is DFS sequence, and the number of accepted solution now falls sharply, only 16. And Ajinkya is its author, and he will explain the solution.
Yeah. So yeah, before we go into the solution, let me firstly quickly explain what the problem was. So we were given two DFS sequences for a tree, and again, the DFS sequences need not be same because at each point during the DFS, we had a choice as to which child needs to be traversed first during the DFS. So based on the order in which the nodes were traversed, the DFS sequences could have been different. So two DFS sequences were given to us, A and B, and we were to say what is the number of trees that rooted trees that can produce both these DFS sequences. So yeah, that was the question, and let's try to see how we can do this. So basically the first point to notice was that the DFS sequence for a tree is basically the root followed by the DFS sequences of each of the subtrees of that tree. So every subtree must appear as a consecutive subarray in the DFS sequence. So to begin with, without worrying much about the space or time constraints, we can think of some recurrence where tree ijk can denote the number of trees, where with the DFS sequence, which begins at I in the first sequence and which begins at j in the second sequence and has a size of k. So we have to count the number of trees. So the answer is basically just tree of 1, 1, n. That means we start at the first element of both the sequences and the subarray has a size n. But again, looking at this recurrence, we may feel that there are some things that might go wrong, right? Because say we select a subarray that begins at I and has a size k in the first sequence A, but these elements might not be connected in the second sequence, right? When we consider the sequence B. So it might look like this is not as easy to solve. So yeah, how to do this? Let's go to the next slide. So yeah, that's actually not a major problem because the recurrence can itself handle such cases. So we just have to make sure that we will call a subproblem only if that can result in some valid answer. But again, what to call valid and all that. So yeah, let's try to simplify this further. So yeah, let's try to define something like T of ij, where this tree of ij denotes the number of trees with a DFS sequence that in the first sequence A, it lies in the subarray from I to j, and it has a DFS that appears as a subsequence in array B. So again, considering a recurrence of this kind, the answer is still tree of 1, comma n, because we have to consider all the trees that are represented by the first sequence A. So yeah, let's try to improve this further. So can we go to the next slide? So yeah, for our convenience, let's define two recurrences like these. So the first one can be tree of ij, where This denotes the number of trees with DFS sequences that are represented by the subarray ij in sequence A, and that have a DFS that is a contiguous subarray of B. Note that we are now considering only contiguous subarrays, but that is fine, because if it's actually a subarray, if it's actually a subtree in our original tree, then it should appear as a contiguous subarray in both A and B. So we define tree of ij this way, and then we define another recurrence called, say, forest ij, which will denote the number of forests with DFS sequences that are denoted by the subarray I to j in the first sequence, and they have a DFS that is a subsequence of B, as we had also discussed previously. So yeah, let's try to see how we can actually try to solve these recurrences. So yeah, let's move on to the next slide. So yeah, if keeping these definitions in mind, the recurrences are now actually more straightforward to consider. So let's try to see how we can define the first tree ij. So note that this will be 0 if aij is not present as a contiguous subarray in B, because that's how we had defined tree ij to be, because that should have been a contiguous subarray in B, and if it's not, then the answer would be 0. And the second condition where again this could be 0 is when some AI appears after some AK appears after AI in the second sequence. Why is this the case? Because if that AK has appeared after AI in the first sequence, then it means that it is in the subtree of I. But if it comes before that element in B, that means that's not a valid case. So again, this would be 0 here. And if both of these are not the case, then we can actually try to form a subtree here. So we will fix the ith element as the root and then try to find the number of forests in the remaining subarray. So let's try to see how we define this forest recurrence. So if we want to find the number of forests in the range I to j, we try to break at every point k such that the subarray from I to k will now denote the first tree in that forest, and then we try to find the number of forests in the remaining part of the subarray. And again, the base case is when there is a single element, the number of forests is 1. So we are trying all possible cases. So all the possible trees that are achievable through this will be considered here. And yeah, since tree of I comma k becomes 0 whenever the case is invalid, so there shouldn't be a problem while calculating these recurrences as well. So yeah, can we move ahead? So yeah, now each of the state again can be calculated in linear time. So there were two things basically that we were checking while calculating tree of ij. Firstly, we had to check whether a subarray ij is also present as a contiguous subarray in B, and that can be done in linear time. Also, we have to check if some element appears before another one in the second subarray. Again, that can be done in linear time. And the sum of forests ij also can be computed similarly. So there are n square states, and each of them can be computed in big of n time. So the overall complexity for this is cubic in terms of the number of nodes that we had, which would pass in the given time. So yeah, that was basically what was expected here.
Thanks, Ajitya, for the explanation. So the next problem is Blizzard Blitz, and there are only 12 accepted submissions for this during the contest. It will be explained, its author and explanation both will be given by Kevin.
Okay, so
Yeah, Kevin, you can start. We can hear you.
okay, sorry. Okay, so hello everyone. I'm here to explain Blizzard Blitz. So it's a problem on a grid where each cell is either ice or snow, and on ice cells you slide, and on snow cells you stand on. So the problem is you want to visit a particular cell, ij, on step k, and you want to find out the number of distinct paths such that that is true. So the first insight here is that the grid is actually very regular. In fact, there aren't any obstacles, so the number of choices you have at any point is actually fixed. All four availables are always all four directions are always available. Actually, after the first step, only three are available because uh, you cannot go opposite to the previous direction. So all in all, from any starting position, there there are exactly 4 times 3 to the n minus 1 possible paths. Okay, next slide, please. So the idea is we want to find the number of paths that go through ij at step k. But as we have seen earlier, you always have 4 available directions, or 3 after the first step. The idea is to reverse engineer the starting position. Since we know that we will visit the cell ij at step k, we know where we probably are, or where our vicinity will be around step k. And we just reverse engineer to find the starting path. We don't actually do the reverse engineering. We just know that it can be done in most cases. And we probably should intuit that for every sequence of directions, there's probably only one starting position. Because as I said, there aren't any obstacles in the grid. And all the steps are reversible. Okay, so what I said, there's only one starting position for every direction sequence. That's not exactly true because there are some edge cases that we need to handle. So next slide, please. So the first cell is, so let's consider the case if ij is ice. If ij is ice, then you can only slide through it. And that means you have to slide through it in between 2 snow cells. Of course, there are still 4 directions on how you do it. And they can be classified into 2 types, vertical or horizontal. But those are not necessarily possible. For example, if the column of ij does not have any snow cells, then you cannot slide through it in a vertical manner. And similarly, if the row doesn't have any snow cell, you cannot go through it in a horizontal manner. But other than that, there are actually no more restrictions. So there are 2 ways to go vertical, 2 ways to go horizontal, and that fixes the direction of step K. Everything else can be chosen arbitrarily as long as we don't choose 2 opposite directions consecutively. So therefore, there will be 3 raised to n minus 1 choices. And the answer will be 3 raised to n minus 1 times this conditional factor. So if vertical is possible, we add 2. Otherwise, we don't add anything. And the same with horizontal. So that handles the case where ij is ice. So next slide, please. So the second case is when it is snow. This case is very similar, except we don't have to worry about column I and j having a snow cell because ij is a snow cell itself. However, there's a different issue because based on the definition of step K, some cells may be visited on 2 consecutive steps at the same time, in particular if it is an endpoint. So in this case, ij can be an endpoint. So there are additional paths aside from the normal paths where you end on ij where you end on cell ij at step K, but not begin there. So we need to include those paths as well. And that can only happen if there's another snow cell where you can come from, or to do that path. So it can happen, for example, horizontally if there's another snow cell at that column, and similarly for horizontal. But other than that, just as in the previous case, there are still 2 times 3 raised to n minus 1 possibilities. So the formula is very similar, except now we add a 4 because that counts the paths where you start at cell ij on step K. So the idea behind this problem is that the grid doesn't have actually any obstacles. So you're basically doing some specialized counting around step K, and that's basically all your constraints. So yeah, that's the solution. Each query can be answered in log n time. All right.
Thanks, Kevin. Yeah, so the next problem is the lag, and there are only 3 accepted solutions for this, and Kshitij will be explaining it. Its author is Kevin.
In this problem, we are given a tree and we are also given many pairs of nodes. So there are many Q queries, and in each query, 2 edges are disabled. And so we have to find the number of pairs of nodes which were given to us initially in the input, such that on their path there is at least one out of the 2 edges which is disabled. So let A be the set of the pair of nodes such that the part between those pairs passes through edges 1. And let B be the same but for H2. So we want to find the size of the union of the set A and B, which is the same as size of set A plus size of set B minus size of set of A intersection B by inclusion exclusion. So let the edges in the query be x1, y1 and x2, y2, where x1 is the parent of y1 in the tree and x2 is the parent of y2. There are 3 cases. The first case, y1 is not the parent of x2 and y2 is not the parent of x1. So their subtrees below the edges are disjoint. In the case 2, y2 is the parent of x1 and in case 3, y1 is the parent of x2. Cases 2 and 3 are exact same type with the edges flipped. Also knowing how to handle case 1 gives all ideas needed to solve cases 2 and 3. They are very similar. So I will be explaining case 1. Next slide. So the insight is we perform a DFS and store the start and end time of each node. Then J is a descendant of I only if the start time of J is included in the range start to end time of node I. Now A intersection B is basically the number of pairs of node AJ and BJ such that AJ occurs in the subtree of Y1 and BJ occurs in the subtree of Y2. Formally, these 2 range conditions given in the slide need to be satisfied. So we will define a function with 4 variables with respect to the above point, which is the number of pairs of gamers such that the start time of AI is included in the I2J range and start time of BI is included into K2L range. Note that these 2 ranges I2J and K2L are not intersecting. So now A intersection B can be very easily written as this formula: F start time x1 end time y1 start time x2 end time y2. A and B can also be calculated very easily using the above function. So you can read it here. Now next slide. So now we need an efficient way of finding this function. Note that if we notice this function Fij, L, this is same as writing F0jkl minus F0I minus 1kl. So like we we manipulate the function based on the time. So we will iterate the node in the order of their DFS, and if we visit a node, if it in the initial given nodes it is in a pair with another node j, we will increase the value of the start time of j in the data structure. It can be either binary index tree or segment tree by 1. So now we can do all the queries of the form F0jkl, which is the same as finding the sum of the range from K to L when we have just finished processing node J in the DFS. So we will be doing all the calculations offline and maintaining some arrays with coefficient -1 or 1 and add them to the answer of the specific query. Next slide. Yeah, so it's done.
Thanks, Kshitij. And now the next problem is cubical romance. We actually expected more accepted solutions for this one. And interestingly, even though there is only one solution, the team that solved it was not in like the top, even I think even in the first page. So yeah, I think it was something that was missed by the top teams. Its author is Kevin, and it will be explained by him.
All right, thank you. So in this problem, you're given a bunch of numbers and you want to find a permutation of the numbers that is cubic. That is, there's a cubic polynomial that generates the numbers. So one common or one well-known thing about cubic polynomials or sequences of numbers generated by polynomials is that usually a few consecutive numbers are enough to generate the whole sequence. For example, if you have a quadratic sequence, you only need 3 consecutive numbers to generate all the numbers, the infinite sequence to the left and right. So in our case, we want a cubic polynomial, so we only need 4 consecutive numbers. So if we can find 4 consecutive numbers, we can generate the whole array. Using, for example, the recurrence above. That recurrence can be computed for any degree. That basically just involves binomial coefficients. So the first step to solve this problem is actually to try something simpler. Instead of trying cubics, try quadratics first. So this is a bit easier. We only want 3 consecutive numbers. And we also know that degree 2 polynomials only look like one of these things, either a parabola opening up, or a parabola opening down, or a line. Okay, and we can see that the hardest part is probably discovering or solving the parabola case. So, okay, so that's the classification. Next slide, please. All right, so we know the 3 cases: parabolas opening up, down, or just a line. Okay, so how do we find 3 consecutive numbers? One conspicuous point in a parabola is its vertex, because that contains the smallest numbers. So that suggests to us to look at the smallest numbers, because those numbers will probably be consecutive. And indeed, that's the case for a polynomial of degree 2. For example, if your range contains the vertex, then the 3 smallest numbers will probably be near that vertex. So using those 3 smallest numbers, you can actually generate the whole array now. Of course, you don't know the order yet, but since there are only 6 possible orders, you can just try them all. So similarly, for the other cases, you can do something similar. Okay, so we move on to cubics. Cubics are a bit more complicated because the shapes are far more varied than just a parabola. Even a degree 3 polynomial has multiple possible shapes. For example, it can have 2 humps, a local maximum and a local minimum, or it can have no humps. And that makes things a bit more complicated. Our previous solution of finding the smallest numbers may not work anymore because of these weird shapes. It's not quite as regular anymore as parabolas. All right, next slide, please. So the insight here is actually, it's not that bad, really. Even though the smallest numbers are not anymore collecting in a single place, it can still only collect in 2 different places, namely one of the ends and one of the humps, and nowhere else. Therefore, next slide, please. We know how to find 4 consecutive numbers because 4 out of the 7 smallest numbers must be on the same place where they collect. Therefore, take the 7 smallest numbers and 4 of them will be consecutive. And then for every choice of 4 numbers, just try all permutations as the order. You can cut the number of permutations in half because reversing the array is equivalent. So actually, that's the solution. there are only around 420 candidates to try. And for each candidate, we can check if it works in linear time by using something like a map or something. All right, next slide, please. So I said the constant is around 420, but in practice, that constant is actually much smaller because you can stop the check if you immediately know that it fails. And with great likelihood, most choices for the four numbers will actually fail because cubics are not that flexible. So I think that's to be expected. Anyway, there's a way to trigger the worst case on some solutions, which is, for example, this case where they're all ones except for a single element. So a naive solution will try all possible collections of four numbers out of the seven smallest numbers, and they will all almost generate the whole array except for one, which will fail. Therefore, it will generate the worst case of 420. So this one is easily fixed though. Just try distinct elements, or I mean distinct collections of four numbers. Don't repeat what you've already done. All right.
Thanks, Kevin. The next problem is dice climbers, and there were no solves during the contest. Its author is Vaibhav, and he will explain the solution.
Okay, so a brief overview of the problem. So there are two players, both of whom initially are at the starting position, which is 1,1. And the first player to reach the mth stair wins. And the game plays such that a player rolls a dice and moves ahead by the number shown on the dice. And if the player lands on a cell where the other player is present, then the other player has to go back to the starting cell. And we want to find the expected number of moves in which the game gets over. So here let's represent E of xy as the number of expected moves if the locations are x and y. And it is x's turn to play currently. Then we know that, let's say the max of x comma y is m, then the expected number of moves is 0. That is our base case. And otherwise, we have 6 other states that we can transition to, say xi, yi, where I goes from 1 to 6. So the probability of each transition is 1 by 6. And the expectation x comma y can be represented as 1 plus 1/6 of the sum of the expectations of the parent states. And the one here counts for the move that is currently being played. Next slide, please. Okay, so in this case, we can see that there are m square possible states. Hence, we have m square linear equations where, as we saw in the previous slide, if the max of x comma y is m, then the expectation is 0. Otherwise, it is 1 plus 1/6 of the sum of the parent states. We can solve this using Gaussian elimination, or in junior college also, you must have learned the row echelon form if you haven't heard of Gaussian elimination, but they are the same thing, more or less. So yeah, it is not a very difficult concept. If you have some m square linear equations here, it would take m square cube time, which would be big of m power 6, which is clearly too slow for our constraints. Next slide, please. Okay, so let's come to an important part of the problem here. So in case there were no cycles in our state transition graph, we could have just applied dp and solved for expectation. However, in our scenario, there are some cycles. An important observation here is that the max of x comma y doesn't decrease, because as soon as, let's say, a player ends up on a state on which another player is already present, the other player goes back. So yeah, in no scenario would it happen that max of x comma y decreases. Hence, what we can do is that we can fix a particular value of max of x comma y and solve for that in decreasing order. So we can start keeping the max of x comma y as m and gradually solve it for all values from m to 1 and compute the expectation for all of these values of m. Next slide, please. So in this case, we know that there would be big of m states overall that we would have to solve for. And we are solving for each value of max of x comma y. So hence that would take big of m cube per value of m. That would be big of m power 4. However, that would be too slow for our constraints as well. So here we can observe that we can only compute the expectation for x which are less than y. And so we can split it sort of into two scenarios. So let's consider the expectation as 1 plus 1/6 of summation of the parent states, which we can represent as e of xi comma yi. Then we can expand e of xi comma yi using its own equation. Let's say it depends on certain xij and yij. So we can show that we only need to expand at most one layer in order to solve this equation for xi greater than or equal to yi. And we can solve this using dp. This would still take big of m comma 4, m power 4, but it has a smaller constant factor. Next slide, please. Okay, so this is one of the crucial observations in this problem. So for the remaining states where x is less than y, where y is a fixed value of m, we can observe that the matrix is quite sparse and we don't need to do all big of m cube operations. The structure is very regular. As you can see that the 7 diagonals that are marked in yellow here and the last 6 rows, only those are the ones that would give us non-zero coefficients. So we only need to solve for those instead of the entire matrix. Next slide, please. So we can exploit this structure and basically perform Gauss elimination only on those last 6 rows. So overall, we would get a complexity of big of m into d square, but that would be per m. So overall, that would give us a complexity of big of m square into d square. And that fits into the constraints that we have provided in the problem. Next slide, please. Okay, you can further optimize this and solve it in big of m square into d by noticing that if the fixed value of the max of x comma y lies between d and m minus d, then the states are acyclic. So we can just do dp on them instead of solving the equations. So yeah, but that was not required in our in the current state of the problem. Next slide, please. So in general, the takeaways from this problem are that let's say you are given a Markov chain, such as in this problem. You use some way to solve a linear equation system to get some properties about it. Usually, you would find a lot of expectation problems that exploit this. And having insights such as you might have certain SCCs which you can solve for in reverse topological order can help optimize time because there might be scenarios where the graph is sparse. Hence, you need not apply, you need not solve the equation for all states in your state transition matrix. And in the extreme case, the Markov chain is acyclic and hence you can just straight away use dp to solve this. Yeah, that's all for this problem. Thank you.
Thanks, Vaibhav. Yeah, so the next problem is the cat, and there were no accepted solution during the contest. The pick here cat is Vichitra's cat, which was the inspiration for the story. And yeah, so the author is Kevin, and he will explain this solution.
Okay, thank you. So the cat is probably the hardest problem in this set. And I won't explain the problem, and I'll just go through the solution, or at least the main ideas of the solution, and not go through them in much detail so that you have the opportunity to fill in the gaps yourself and attempt to solve it, because I think that will be very satisfying. All right, for this editorial or for this solution presentation, we will use a straight arrow to mean an edge and a squiggly arrow to denote a path. So first thing is we want to characterize what exactly the decisive graphs are. So we want a simple criterion that is equivalent to being decisive. So the first step is to start at an edge. And since the graph is decisive, there must be a path back from y to x. And together, they will form a directed cycle. So that's the first part of our graph, but that's not necessarily the whole graph. Okay, next slide. So the next step is to choose another edge. If the if the if this is not the whole graph yet, then there must be another outgoing edge. Let's say z to w. And since the graph is decisive, there must be again a path back from w to z. This path goes back to the cycle at some point, but where? There are multiple nodes in the cycle. I claim that it must return to z itself and not any other node. And the simple reason is if that's not the case, then there will be two paths between some pair of nodes. I think you can fill out the details. Anyway, so therefore, what happens is the path returns back to z, and so we now have two cycles that has a single node in common, namely z. Okay, next slide. So we just repeat the argument until we get the whole graph. So while our current subgraph doesn't contain all the edges yet, just find another outgoing cycle, outgoing edge, and using exactly the same argument, you can show that it returns exactly at that node again. Therefore, from our current graph, we adjoin another cycle that has a single node in common. And we can do this until we get all the nodes of the graph. So therefore, we now know what a decisive graph looks like. It must consist of several directed cycles that are conjoined at points, and they form a tree-like structure. It's kind of like a cactus. So next slide, please. So here there is an example of a decisive graph, and it kind of looks like a cactus graph, except the edges are directed. So keep this in mind while you're trying to find properties of decisive graphs and solving the problem. This is what our graph should look like in the end. All right, next slide. So the next step is to solve the problem itself. We want to add edges so that our graph looks like this. So we first check the strongly connected components, because the strongly connected components, they must be of this form already, because there must be a path between every two nodes in a strongly connected component, and there must be exactly one path. So if we find an SCC and it doesn't satisfy this property, then we immediately output 0. And the condition can be checked in linear time. All right. So what about the remaining edges? The remaining edges will connect to different SCCs. Okay. So for the following, we will define the SCC graph as the graph where each SCC has been shrunk to a single node. Okay, next slide. So my claim is the remaining edges actually form a tree among the SCCs. In other words, if there are C strongly connected components, then there are exactly C minus 1 edges connecting different strongly connected components. Okay, so in other words, it looks like a tree, except it's not really a tree because the edges are directed. But if you ignore the directions, it will look like a tree. All right, next slide. So the proof is, I'll go through this quickly. If it's not a tree, then there will be a cycle, except this cycle is directed because each edge actually has a direction. However, the simple cycle will not be an actual cycle because we assume that the cycle goes through nodes from different SCCs. However, in a decisive graph, that's impossible. If you remember our earlier picture, there are no cycles there that are not directed cycles. You cannot find a simple cycle if you ignore the direction that is not a directed cycle in the original graph. So that's basically the proof. So next slide, please. So we now know that among those edges, there are no cycles. Therefore, they form a forest on the original nodes. They only form a tree among the SCCs, but remember that we shrunk the SCCs earlier. If we unshrink those SCCs, then the C-1 edges will form a forest among those nodes. Okay, we now need to add edges, additional edges, so that the whole thing becomes decisive. And we now know that the remaining edges form a forest. Okay, next slide. So the next observation is the additional edges we add must connect nodes from the same tree of this forest. In other words, if you look at the non-SEC edges, then we should never add an edge that connects two different trees. So why is that? I won't give the proof here, but the insight is essentially the same as in the previous proof, which is you cannot find a cycle that is not a directed cycle originally. So the proof is quite simple once you get familiar with decisive graphs. But after knowing that, that actually makes our lives simpler, because that means we can solve for each tree separately. We find the number of ways to turn each tree into a decisive graph, and then we just multiply all those answers together. Therefore, finally, we have simplified our problem so much that what we're left with is a tree. All right, next slide, please. And this is the final part of the solution. And I think I won't actually give the answer here, because if you were able to follow up to this point, I think you can fill in the details of this remaining part. This is, I think, one of the easier parts of the problem. I just leave hints here. So the first hint is choices can be made per node. What the choices are, I won't elaborate here, but when you're trying to turn the graph decisive, you will eventually discover that you will have to make certain choices per node, and you will and my claim here is that you can make those choices independently of other nodes. The second hint is the choices in a node bears a striking resemblance to matching. Okay, after doing all of those, I just mentioned here that the final solution will run in linear time. And that's the solution. I hope you enjoyed it.
Thanks, Kevin. So yeah, that concludes the problem set. And I'd also like to say that if you're not solved any one of the problem, then do look at the solution and upsolve it. That's an important part of learning and progressing in competitive coding. So that's it from the judging panel. Sir, back to you.
So I hope it is over, Bala.
Yeah, yes, sir. The session, the problem discussion is over.
Okay. So again, I am not sure if winners are watching this, and we will. So there are a lot of questions in with regard to the distribution of the slots. Then whether we will have Asia West this year. No, there is no Asia West this year. Then T-shirt we will be dispatching it soon, maybe in next 2 or 3 weeks time. We need some time. Then distribution of the slots is completely decided by the ICPC headquarters and Asia West director. But that also will be soon today, and we will be releasing the final rank list maybe in 1 or 2 days time. So again, thanks the judges, the problem setters, the Bala, and the entire crew behind this ICPC Asia Amritapuri 2020 regional contest. And we will certainly announce the next contest, that is the ICPC 2021, which you have been waiting. most probably by end of October, because that by that time only the world finals will get over. And we are also coming up with another contest called as Indian Sports Programming Championship. We used to host till 2019. Amrita would like to resume it again on the same Codrills platform. So we'll soon hear about these 2 or 3 contests. Thanks again. Keep participating in the contest. Then sharpen your problem solving skills, and all the very best for your future. Thank you. Thanks a lot.
Hi, my name is Ruslan, and I have been an intern with IBM Quantum this summer.
My name is Yeva. My research at IBM focused on studying pharmaceutically important reactions using quantum computers.
Hi, my name is Rachel Lee, and I'm currently a sophomore at Harvard studying computer science and statistics.
I'm Ramnik Tautanamo here to talk about my IBM Quantum internship experience.
Going for an internship at IBM Quantum was a no-brainer for me.
Implementing configuration management functionalities to the QTracker tool.
I knew very less about quantum computing and I just wanted to give it a try.
The Kiskit Summer School, I learned so much about quantum computing that I hadn't known before. And it was just definitely a deep dive into theory, helping me to learn more about the complex math that underlies quantum computing and all the technical details that go into creating quantum circuits and quantum hardware.
It looked encouraging for me to apply, to work with IBM Quantum, and I am humbled to have had this opportunity.
It's a world-class science and it's done by world-class groups.
This internship has definitely changed my future plans.
I realized that IBM offers this really great and unique space in between academia and industry for people to research. And so I'm definitely also really excited to explore that as a potential career option in the future as well.
My name is Tejas Sachdeva. I'm a recent graduate from CSU Channel Islands. Ever since I've been a kid, I've always been into technology. I've kind of been the person around the house who's always fixing things, playing with gadgets. So that's always been an interest of mine in technology. And when it came time for me to choose a major in college, computer science was the one. My professor actually told me about AWS Educate and how he was using the platform to teach students about cloud computing. So that was really exciting for me. And that's where my journey started with AWS Educate. It was like a cloud computing 101 course for me. None of my classes in college were really about cloud computing. So I wanted to see what it was about, how it's being used in the industry, and what are the career aspects of it. 90% of companies use some aspect of the cloud. That is huge. I can take the skills that I learned here and apply them anywhere. As soon as I got exposed to AWS Educate and I got my cloud practitioner certification, it exposed me to so many different opportunities, both job-related and networking opportunities, which in the end led me to this great position at AWS Educate. I'm currently the program manager intern on the AWS Educate employer team. So my task is to mainly help students get employed. Having gone through the AWS Educate program has put me in the perfect position to help future students because I was in their shoes not just a few months ago. Working on the Educate employer team gives me a unique lens into the program, and just in my first 6 weeks I've been able to make changes to the portal which allows a better student experience. The opportunities with AWS are endless. If you're a college student, just dive right into AWS. It's free for students. You can take the Cloud Computing 101 track and just immerse yourself in cloud computing. Don't think twice about it, just go down this road. At the end of the day, you get to learn something new, which you can apply to other areas of your life as well.
Hello, my name is Mikhail Dvorkin. I am 2007 ICPC Gold Medalist and Kotlin enthusiast. In this short video, I will be using Kotlin to solve a sample algorithmic problem that appears sometimes on coding interviews. This problem will concern finding dictionary words inside the rectangle filled with letters. Let's go to an IntelliJ IDEA window to discuss the problem and solve it in Kotlin. First of all, I'd like to thank Solontus_ and Lalit Kundu for bringing up this problem on different websites. So the problem is we have a rectangle filled with English letters and a set of words that we will call dictionary. And the question is, which of these words can be read in this rectangle if we are allowed to read horizontally or vertically and turn 90 degrees as many times as we want. For example, in this rectangle, we can read the word Kotlin or fun or file according to these rules. Let's hard code the rectangle with letters into our program. So this will be a row string with all these tabs and line feeds that we will deal with later. And the dictionary will be also stored as a row string that needs some processing as well. The rectangle row string has all these tabs and line feeds, so let's first remove the tabs by trimming all the indentation of the string. And now we have a single string with letters and line feeds, so let's split the string with a line feed character to receive not a single string, but a list of strings that are horizontal lines of the original rectangle. We can print the resulting variable to make sure we got our trimming right. And now for the dictionary line, let's make sure it's uppercase, just as all the letters in the original rectangle. And now with this uppercase single string, we can split it by a comma and a space to receive the list of single words of the dictionary. Actually, knowing that I want a lookup operation in this data structure to be quick, I can make this a set. Now let's actually code the method that is going to do the main work. I propose a recursive implementation over here, so let's discuss the signature of our method. For now, let it receive the coordinates of the cell that it is currently processing, but we will update the signature with some more arguments later. When we enter an instance of this recursive method, we are standing in the cell with coordinates x and y, and in general case, we want to make a recursive call into each of the 4 neighbors of this cell. How do we organize the iteration over all 4 neighbors of this cell? Well, I propose a list of vectors that show the directions towards all the 4 possible neighbors. In this list, I will be using Kotlin pairs to store the direction vectors. Now, in the recursive call, I can iterate over all the possible shift vectors, and in this for loop, I will be using multiple variable assignment to introduce 2 variables, the x shift towards the new neighbor and the y shift. With these 2 variables, I can calculate the coordinates of the next cell that I will visit in the upcoming recursive call. We have the new x coordinate and the new y coordinate, but these 2 coordinates can show outside the rectangle, in which case I want to ignore this iteration of the for loop as this shift vector is useless. Also, I definitely want to know the letter that is located in these new coordinates if they indeed show inside the rectangle. So let me write the code that does these 2 things simultaneously. I could have written a simple code that makes a direct access to the 2-dimensional array by the y coordinate and then by the x coordinate. But this code raises an exception in case a y coordinate or an x coordinate goes outside the rectangle. So let me rather use nullable objects here that Kotlin handles so nicely. And instead of taking the horizontal line with such index, I will rather use the getAllNull method that will give me the horizontal line with such index or null in case this index is invalid. For this object, I want to do something only if this object is not null. So I put a question mark here, and then I apply the same method to receive the value in the certain index or null if this index is invalid. This object is the letter located in the desired coordinates or null if at any point the y-coordinate or the x-coordinate was pointing outside the rectangle, in which case I want to disregard the entire iteration of the for loop, which is exactly what a continue operator does. So if I have reached this point of code, then I didn't run the continue operator, and therefore my coordinates are showing to the actual cell and not outside the rectangle. So I can make a recursive call to these new coordinates. So over here I make a recursive call to the new cell that I'm sure is not a place outside the rectangle. However, this resulting code is an awful example of the infinite recursion, because each instance of my method always runs several other instances of the same method for the neighboring cells, and they do the same recursively, and so on and so on and so on. So we need to stop our recursion at some condition. In order to do this, let's change the signature of our method so that it receives the word that has been already read during the previous recursive calls. With this word, we can stop the recursion if this word is not a prefix of any word in the dictionary. We need to pre-calculate before the recursion the set of all the prefixes of all the words in the dictionary. Let's take our dictionary, and I could have used the map method to receive the list of lists of all the prefixes of the words in the dictionary. But what I actually need is the concatenation of such lists. So instead of the map method, I will use the flat map method that will do exactly the thing. Inside this flat map method, I want to receive the collection of all the prefixes of the given word. So let me introduce the word variable that I will be working with. And here I need to construct a collection with its prefixes. It will be a list, and the length of this list will be the length of my word plus 1. And for each index, I want to generate the prefix of my word with the corresponding length. So from my word, I take the corresponding number of letters. And once again, since I want the lookup operation to work quickly, this overall collection should be rather taken as a set, not a list. Now let's get back to the recursive method. In case the already read word is not a prefix of any valid word in the dictionary, just disregard the entire recursive call. And if the current read word is exactly a word from the dictionary, let's print it to the answer. And the recursive call to the neighboring cell should also pass the correct argument to the method. So it will be the already read word plus the letter that we have seen in the new cell. Now we are ready to make a call of the recursive method for each cell of the rectangle. In order to do this, we iterate over all the possible values of y-coordinate, and instead of writing the specific lower and upper bounds, I'd rather write the indices of the rectangle because this is exactly the values for y that I want to iterate over, and I will not make a mistake by +1 or -1 in such code. Now, for the x coordinate, let me also write some code that will be safe from +1 or -1 mistakes. So these are the indices of the horizontal line, for example, number 0. And for each y and for each x, I make a call to the method search with these two coordinates, and the word that I start with is the word consisting of a single letter in these coordinates, passed as a string. These for loops will run the recursive search from each starting point, and these recursive searches will print all the found words to the output. So let's run this code to find all the words in our rectangle. And we see that our rectangle contains all the words from the dictionary except for the word null. The basic problem is solved, but the important exercise yet to be done is to forbid ourselves from coming to the same cell several times, because it's a very natural thing to disallow, and our code still allows such behavior. So I leave it as an exercise for you, or probably we will do this in some other later video. Thank you for watching this video. Have fun using Kotlin and other programming languages, and good luck in your careers. Bye.